So in this section, we've been looking at volume by slicing, and that gives us the opportunity to look at, let's say, a loaf of bread, slice it into small pieces and stack the areas up against each other to get a volume. So the two problems that we're going to finish for volume by slicing are as follows. Here is the first one, and it reads, the base of a solid is bounded by the curve y is equal to the square root of x and the line x equals 4. The cross sections perpendicular to the x-axis are squares. Find the volume of the solid. Okay, so we're going to work on example 1. I'll give you a few minutes, a little minute or two to write it down. And I'm going to go back and add one more step to my original steps from before. I don't know how I forgot this step, but the most important step is, if you can, draw the region, draw the solid. So we're going to try to draw this thing. Okay, so the first thing I want you to do for example 1 is draw the base. What does the base look like? So draw the base in the XY plane. Draw the base in the XY plane. So we're doing volume by slicing. Okay, so when we draw our base in the XY plane, actually, I don't even need that much. So this is example 1. So when I draw the base in the XY plane, my base is the square root of x. So here is y is equal to the square root of x. And then it goes between, actually, it's even flatter than that. It's a little flatter than that. Okay, and it's between x, and it's also bounded by the line x equals 4. So if I draw the line x equals 4, then you can clearly see what the base of my region is. So this right here is the base. Okay, so now if I were to draw this thing in 3 space for a moment, I would have on the XY plane, this is the line y is equal to the square root of x. So that's it on the XY plane. And then the line x equals 4 looks like that. So as you can see, in 3 space, I've drawn my base. So again, this is the base. And so now it tells me that sticking out or sticking up in the air are squares. Okay. So they are squares. So the cross-sectional areas are squares. So that means that if I were to draw, just draw any line, let's say draw here. So here is my, so I choose this value of x. And for that value of x, what is sticking up out of the plane are squares. So as you can see, that is the area of my cross section. So the area of my cross sections are squares sticking up. All right. So we said that in order to do this integral, the integral for volume by slicing is the integral from A to B. I need to know what my area is, because I am adding up, that's the integral, all of these different areas. Okay, so the areas are these squares. All right, so that base of that square is the same base of the square that is right here. So this is the bottom part of the square. That is the same square that is in the three-dimensional picture, but that's the bottom part. Okay, so if this square were sticking up in the air, it would look like that. So that is my squares. They are cross-sectional areas. They are perpendicular, as you can see, to the x-axis. Okay, so what is the area? So what I need to now find is I need to figure out my limits of integration. So I drew my picture. What are my limits of integration? For any value of x, where does x start? Go ahead.
Well, based on what I'm seeing, it looks like that the x starts at 2.
No, this line can start all the way over. Okay, so I see what you're doing. Okay, so remember, there are a bunch of slices. There are tons and tons of slices. There are many of these. There are many of these slices here. Okay, so this one is a slice that sticks up. I'm adding up all, this is a slice that sticks up. So where do the slices start?
Do they start at x equals 4?
Okay, that's where they end. Okay, so they're going to go up to 4. Good. Okay, so now I have my value.
So they start from 0.
They
right?
start from 0 and they go all the way up to 4. Good. Okay, because I am stacking these pieces from the beginning of the region all the way up to the end of the region. And so, yes, they're going to start at x equals 0 and end at x equals 4. And then what is the area? So I now still need to find the area. So now the area, so each one of these is a square. So this is my square. And this line right here, this, I'll highlight it. This base, that's the bottom of the square, corresponds to the same bottom of the square here, corresponds to the same bottom of the square there. So how do I know how tall that is? How do I know how high that is?
If it's a square, they have the same sides. So
Okay,
lines,
so
right?
they're going to have the same sides. That is exactly right. But I need to know what that side is. So how can I figure out what the side is? So I chose an X. Where is this point? Where is that point? That point lies on the curve. Y is equal to the square root of X. So for any X, that height is its square root. If X is 4, this is 2. So when X is 4, that's 2. But for any X I choose, if I chose X equals 1, that height would be 1. If I chose X equals 3, that height would be the square root of 3. So for any X I choose, that height is the square root of X. That height is the square root of X. Okay, Ezekiel, you said that it's a square, so what is the other side? Anybody? What's the other side?
Square root of
Also
x.
square root of x.
Also the square root of X. Good. So therefore, what is the area of that region?
X.
X squared.
Great. It becomes the square root of X times the square root of X, which is just X. So this X goes in here, dx. I integrate that, I get 1/2 x squared evaluate it from 0 to 4, and my answer is 8. Okay, done. That's example 1. Okay, so write down example 2. Example 2. So now the base of a solid is bounded by the curve x squared over 81 plus y squared over 9 is equal to 1. Okay. Okay. All right, so let's look at this one. So the base of the solid is bounded by the curve x squared over 81 plus y squared over 9 is equal to 1. The cross sections perpendicular to the x-axis are rectangles whose height is 1/4 the size of the length. Find the volume of the solid. Okay, so what is this curve, x squared over 81 plus y squared over 9? Does anybody know what that is? Does anybody know what that is? Okay, that's pretty scary.
Is that the Pythagorean theorem or no? Or part of the Pythagorean theorem?
No, it's not part of the Pythagorean theorem. It happens to be a conic section. So it turns out to be an ellipse. Okay, so this is my ellipse. So that's what it is. So that's the base. And sticking up out of it are rectangles. Okay, so that means there are rectangles sticking up out of this thing. So the areas, if I choose an X, so here's the X I'm going to draw. Choose that X. Then sticking up out of it are rectangles. Okay, so here's the rectangle. So the cross-sectional area that I have to find is the area of a rectangle. So how do you find the area of a rectangle? That's fairly easy. What is that?
Length times width times height.
Okay, that's too much. It's just the area of the rectangle. It's only in 2 dimensions. So what is that?
Length times height.
Good. Okay, so A of X is just going to be the length times the width, or in length times the width, or in this case, it's actually just like that. So if I were to take that rectangle and draw it flat so I can get its area, here it is. Well, that wasn't it, but here it is. So here's the rectangle. And the side that's laying on the axis, this is the side that's laying right here. So this is the same side. Okay, so we need to find the length of that side. Okay, so now what I need to do is I need to say, well, first off, this thing is symmetric. Whatever it looks like on the top half of the curve, it looks like on the bottom half of the curve. Okay, so I'm going to take this curve right here, and I already know that this curve is x squared over 81 plus y squared over 9 is equal to 1. And so I'm going to solve for y. So I'm gonna multiply both sides by 9, x squared over 81, y squared over 9 is equal to 1. I'm multiplying everything through by 9, so I'm going to get x squared over 9 plus y squared is equal to 9. So that's going to give me y squared is going to be 9 minus x squared over 9. And so therefore y becomes the square root of that thing. Okay, so y is the square root of that. So that is the equation of this curve. So the equation of this curve, get rid of that because that's in my way. So the equation of this curve right here is y is equal to the square root of 9 minus x squared over 9. Okay, so therefore, if I select the x, so here's the x I'm going to choose. If I select the x and I choose to go up this high, how long is that distance? Well, that distance is just the y value because that's how high it is. So therefore, I know that from here, this little piece from here, from the center dot up to this top dot is the square root of 9 minus x squared. So that says to me that this whole length is 2 times that. So this side then is 2 times the square root of 9 minus x squared over 9. So that's how long that side is. So now I can say the length is 2 times the square root of 9 minus x squared. 9 minus is that. Oh.
Dr. Locke, sorry to interrupt, but just for clarification, the shorter part of the rectangle is the square root of 9 minus x squared over 9?
The shorter part? No, the longer part. Okay, so the longer part, okay, do you see the color blue?
Yes.
Okay, so notice how this is the bottom of the rectangle is on the base
Yes.
and the rectangle is sticking out towards you in the page.
Yep.
Okay, so this is the bottom, that same bottom.
Okay. Yep.
So that's the length. So that's 2 times the square root of 9 minus x squared. So what's the height? What's the height? Go back and read the problem.
1/4.
1/4. Okay. So 1/4 times.
So h is 1/4 L. So that means h is 1/2 of that thing. because it is 1/4 of this. So when I take 1/4 of 2 times that, I end up with 1/2. Okay, any questions?
Yeah, I'm not getting how you getting half.
Okay, so I did 1/4 times 2 times that thing.
So you saying it's a quarter, but like, what is a quarter? How do you know it's a quarter?
Oh, okay, let's go back to the problem. So it says the cross sections perpendicular to the x-axis are rectangles whose height
Okay.
is 1/4 the size of the length. Okay. So this down here is the length and this times the height. So we're using length and height instead of length and width because our thing is sticking up out the page. Okay, so therefore, what's the area? So it's going to be 2 times the square root of 9 minus the square root of x squared. And then that's going to be multiplied by 1/2 times the square root of 9 minus x squared. So therefore, the 1/2 and the 2 divide out. I get a square root times a square root. So that's just going to give me 9 minus x squared over 9. Okay, so now here's the trickier part, because now we have the area. So we have the volume is the integral. We don't know a and b yet. So we don't know what a and b are, but we do know the area is 9 minus x squared over 9. Okay, so how do we find a and b? Well, we're starting from this, remember now, notice where this line goes. So this line starts all the way over here. Okay, stop it. It's still not done. Okay, it starts all the way over here. And it starts all the way over here and all the way over here. So it starts at this value and it goes all the way over to this value. So how do I find those values? What do you know about y at those points?
We know y is square root of 9 minus x squared over 9.
That's right. But what do you know about y at this location right here? And y at that location right there? What do you know about y? Look at your graph. At the corners of the ellipse, what do you know about y, guys?
Is it 0?
Yes, y is 0. Y is 0. So I have x squared over 81 plus y squared over 9 is equal to 1, and y is 0. So that says x squared over 81 is equal to 1, or x squared minus 81 is equal to 0, or x minus 9 times x plus 9 is equal to 0, or x is equal to plus or minus 9. So therefore, we can go back to our picture and we can label this as -9, and I can label this as +9. And now I see that this becomes -9 and this becomes +9, and I compute my integral and I get 108 as my answer. Okay. All righty, next topic. Is this in the same section? Let me check. Yes. Okay. So now we will go on to volume by disk. Okay, so volume by disk is very similar to volume by slicing. The only difference is okay, so the only difference is in volume by disk, the areas are always circles. So the integral from a to b of a of x dx, when it's the volume by disk, that implies the area. Whoops, I don't mean that to be a pi. Is always the area of a circle. What in the world is going on? So hold on a minute. This is driving me nuts here. First off, why doesn't that go away? Okay, so what's the area of a circle?
Pi times radius squared.
Okay. So the area of a circle is pi times the radius squared. So basically pi is known. So what we need to identify is we need to identify the radius. Okay, so this is what we're going to do. So we're going to do first revolution of a region about the x-axis to make a solid. So the first we're going to do is revolution about the x-axis. Of a region to make a solid. All right, so let's start off with okay. So again, this is the y-axis. No. No. That's the x-axis. This is the x-axis. And this is the y-axis. And so here's my curve. So my curve may look like this. So this is the curve, y is equal to f of x. So now let's select a value. So we're going to go between some a and b. So here's a and b. It doesn't have to be 0. It could just be here. Let me make a there so it's not necessarily 0. So I'm going to select the x between them. And I'm going to go all the way up here and find the function value. So therefore, as you can see, this, I'm going to take now and revolve this point about the x-axis. And when I revolve it about the x-axis, I end up with something that looks like that. So if I did that with everything, the whole thing would look like this. And so now I'm going to have a solid. So I'm going to revolve this. I'm going to get that at the back. I'm going to revolve this. And as you can see, now I have a solid. It actually looks like maybe a big piece of ham. Okay. And so now you can see that the cross-sectional areas are actually discs. They are circles. So the area that I'm going to be looking at is always going to be a disc because I am revolving it about the x-axis. So my area is always a disc. What I need to now do is find the radius of this disc. Well, when I go to find the radius of this disc, the first thing that I notice is that the radius is just the height. And the height, so this is the radius r. And that for me in this problem is just y of x. So for a simple problem like this, so I want to take a circle, take a curve, revolve it around the x-axis and figure out what's the solid that it makes on the inside of it. It makes this little piece of ham or meat that's there. And if I slice them, all of my slices will be circles and all of the radii are going to be r of x. So my formula is the volume is going to be the integral from a to b of pi. And then I'm going to get the radius of x squared dx. And as I said up here, we have to identify the radius. Okay, so this is the volume of revolution about the x-axis of a region bounded by y is equal to f of x, which is our radius. So I'm going to write y is equal to r of x. On the interval a, b. Okay. Okay, first problem. Okay, so this is going to be example 1. And so why does it say example twice? Okay. So I want to find, so the region bounded between the curve, y equals square root of x, 0 less than x less than 4, and the x-axis is revolved about the x-axis to generate a solid. Find the volume of the solid. So this is the same region we had before, but this time it's being revolved around an axis. So I'm going to take and draw my region. I'll also give you a minute to go ahead and copy the problem down, because I know that I copied the problems early. Xavier never came, neither did Logan. And Antoine's why they marked absent. Okay.
Oh, wait, I'm here.
Where's your camera? Hi, Logan. Okay. So this is y is equal to square root of x between 0 and 4. So I'll draw the between 0 and 4. So here's 4. Okay, so so this is my region. Okay, so if that region was shaded in, so that's my region. So that whole region there is going to be revolved around the x-axis. So that's the region. So therefore now, again, I'm going to find an x in between, find its y value, and then draw my disk. So now that I have my disk, I can now see that my disk right here, it makes a circle. So there's my disk. All right, so now that I have my disk, I need to find the radius of the disk. Well, the radius of the disk is just this height. So that's the radius, and that height is y. equal to the square root of x. So now I know my radius r of x is the square root of x. Okay, again, more circles. This is what more circles would look like. Okay, so as you can see, you can kind of get an idea what the region looks like. All right, and so therefore I can see that this disk starts all the way back at x equal to 0, and it goes all the way up to x equal to 4. So therefore my volume is the integral from 0 to 4 of pi. My radius is the square root of x squared dx. So this is pi times the integral from 0 to 4 of x dx. So that just turns out to be 8 pi. Okay. Okay. So on to example 2. All right, so this one is a little different. This says find the volume of the solid generated by revolving the region bounded by y equals square root of x and the lines x equals 1 and x equals 4 about the line y equals 1. Okay, so let's draw our region. Okay, so y is equal to square root of x again. So I know at, I'm gonna be a little bit more precise. I gotta go between from 0 to 4. So I know at 0, it's 0. At 1, it's 1. 2. At 4, it is 2. Okay, so here's my curve. Okay, so there's y equals square root of x again. This time it says it is cut off by the lines x equals 1. So here is the line x equals 1. Okay, x equals 4. So here's the line x equals 4. And the line y equals 1, okay? So y equals 1. So let's see what y equals 1 looks like. Okay, so now we see our region. So here's our region right in here. This is our region. This stuff right here is my region. So that's the region. Just that little bit. And I want to revolve that about the line y equals 1. So when I revolve that around the line y equals 1, this is the line y equals 1, it's going to come down like this. And for any value of x, I'm going to draw a circle. And this is the radius. That's the radius of my circle. Okay, now this one's a little tricky. I still see my circle, so I still know I'm going to be using, because I'm using the disk, that the volume is equal to the integral from A to B of pi times the radius squared.
I have a question.
Yes.
So for when we're looking for the radius, we can use any value of x that's in the.
Oh yeah, you're just going to choose, just pick your x. And then you see, once I pick my x, I know that my circle starts back here at this value, which is x equals 1. And I know it goes all the way to the end to this value, which is x equals 4. So now I know my limits of integration. I know A is 1 and B is 4.
Okay, thank you.
Okay. So now the hard part for this one is to find the radius. That's a toughie on this one. Okay, so the radius is, if I were to take this height going from here all the way down to there. So for any value of x, this height up here, right here, is the square root of x. So from here, all of this is the square root of x. But this little piece is 1. And I only want this much. So the radius says, take the big long piece, subtract off the short piece, and that will give me the little tiny piece inside the circle. So what I did was I said, I took this long piece where this distance is the square root of x, and then I took this short piece where this distance is 1. And then I said that the distance that I really want, which is this piece, will then be the square root of x minus 1. So that is going to be my radius of my circle. So therefore, r of x for this problem is the square root of x minus 1. We already know A is 1 and B is 4. So we're ready to do this. The volume is the integral between 1 and 4 of pi times the square root of x minus 1 squared dx. Okay, so this is pi times the integral. I really don't need to compute this. Y'all know how to integrate. This becomes 7 pi over 6. Okay. So again, once I drew my region, figured out that I was revolving it about this line. So I'm revolving about this line. So when I revolve it about that line, I now have to figure out what this radius is. That's the radius of the circle. So for any x, to top of the line is the square root of x. And then I'm always going to be subtracting off 1. So that will give me my radius. Okay. So this is the formula for the volume of revolution about the x-axis. So what happens if I'm going to revolve something about the y-axis? Okay. Well, if I want to do a revolution about the y-axis, so now I'm going to have something that looks like this. So let's say this is my curve. Okay. And I want to involve this region. So this is my region. And I want to revolve it about the y-axis. Now, normally we think of this curve as y is equal to a function of x. But to revolve it about the x-axis, I have to write it as x is equal to a function of y. Instead, then I'm going to find a y value, find out what the radius is here, do the same thing as before, draw a circle because I'm revolving it about the y-axis. Then I'm going to get this region. And so now I'm going to need this radius. But that radius, so now the radius is a function of y. And now I'm going from C to D. So my volume is going to be the integral from C to D. I'm going to have R of y dy. And this is the volume of revolution about the y-axis. On the region bounded by x is equal to R of y on the interval C, D. Okay.
Professor, is this a BDD? You said volume of revolution about y-axis of region BDD.
Bounded, bounded. Bounded. That's what I had before. Bounded. BDD means bounded. So now for this particular problem, many of the problems that are in the homework, you may not know what x equals 2 over y looks like. But you do know, so let's start here. You have x is equal to 2 over y. So that implies that y is equal to 2 over x. Now y equals 1 over x looks like this. So that's y is equal to 1 over x. So I expect that y equals 2 over x is going to be similar, but just a little bit bigger. So I'm going to write y equals 2 over x, pretty much the same curve. So this is the curve. Y is equal to 2 over x, which is the same curve x is equal to 2 over y. Remember, I'm not trying to find the inverse. It's the same curve. It's the same curve. I'm just writing x in terms of y. Okay. And it tells me between y is equal to 1. So y is equal to 1 would be here. And y is equal to 4 would be up here. So this is my region. And then I'm going to choose a value of y. Revolve it. There's my disk. And here it is on the other side. So I am trying to find the volume of this thing. So I'm trying to find the volume of that. Okay, well, they already told you that y went between 1 and 4. So this is my C and this is my D. And X says this is my radius. My radius here is whatever my X value is. And that is 2 over y. So now I get that my radius is equal to 2 over y. So now I'm going to get the volume is the integral from C to D of pi times 2 over y squared dy. So I'm going to pull out the 4 pi, get the integral from help me. C is 1 and D is 4. And I'm left with y to the minus 2 dy. And that turns out to be 3 pi. Okay, last example for today. All right, so I have to draw this region for you because you don't have it. So I will draw it. So this region looks like this. Oh my goodness, it's terrible. It's pretty bad, still bad, but okay. And then this, so this is, okay, Dawn, let's try it one more time. One more time. This is y is equal to x squared. And then this is the line x equals 2. Okay, so this is the line. So this is the point O, A, B. So that's the region, OAB. And I'm going to revolve it about the line segment AB. So that means I'm going to take this, and when I revolve it, it's going to look like that. So therefore, this comes down like this, and it goes all the way to the ground. Okay. So this is the point, this is the line x equals 2. So this point, right, this is at height 4. So this point is the point 24. Uh-oh, I got A and B mixed up. Not that it matters, but this is A, it's the 0.20, and B is the 0.24. Okay, and this line is y is equal to x squared, and that's the line x equals 2. So when I revolve it around the axis, you can see my disk. So there's my disk. So I already know I'm using volume by disk. I know I'm going to get, and my disk is horizontal. So therefore I'm going in the y direction. CD of pi times r of y squared dy. Okay, so I need to find the radius of this thing. So here's my radius. I made it red, I can make it green. There's my radius. Okay, so now I just need to know how long that is. All right, so my radius says, well, I have to take whatever this curve is, this one here, and subtract this curve. So I'm going to take the top curve. So if I get this minus this, that will always give me my radius here. Okay, but now this is x is equal to y squared. It's not a function of y. So I need to change that to x is equal to the square root of y. So now this helps me. So now I have this. So notice what I have, guys. I'm just going to draw it real quick. Okay, so this is x is equal to 2. And then I have, this is x is equal to the square root of y. So now notice if you take this length, which is x equals 2, and you subtract this part, then you're only left with that part, which is what I want. So therefore, my radius is going to take 2 and subtract the square root of y. And now C and D, well, my disk, this disk starts all the way down here at 0 and goes all the way up to 4. So my volume becomes the integral between 0 and 4 of pi, and my radius is 2 minus the square root of y squared dy. Since this is the last problem, I'll go ahead and just do this, take the pi out, the integral between 0 and 4. When I square this, I'm going to get 4 minus 4y to the 1/2 power plus y dy. Okay, so that's going to give me pi. I'm going to end up with 4y minus, I'm going to add 1 to this, which is going to give me 3/2. I already have a 4, so I'm going to multiply by 2/3 y to the 3/2 power. And this is going to be 1/2 y squared. Evaluate between 0 and 4. And this comes out to be 8 pi over 3. Okay. These take practice. It is impossible to do these on an exam if you have not set them up and integrated them yourself. And on the exams, you don't have homework problems sitting next to you. So you have to be able to do these independent of homework problems that are sitting next to you. Okay, any questions?
Are there any practice tools online that can be helpful in understanding how to do cross-sectional equations or processes of how to go about it?
The cross-sectional one, this in general, or this topic in general, or do you mean just the slicing, or do you mean this whole topic?
Slicing and also the like revolutions for both the X and Y axis.
Okay, I can find some links for you and put them up.
Okay, thank you.
Okay. All right. Okay, everyone, I will see you tomorrow. All right.
Can I speak to you at the, can I speak to you?
Thank you.